from Indian Institute of Science, Bangalore, and he was the Vice Chancellor for Defense Institute of Advanced Technology, Deemed University, Pune, and he is now today going to address us on the latest trends on advanced computing. It is a special privilege only for IEEE student branch members that here such an esteemed person is there with us who would be addressing you. So please give him a round of applause.
So at the outset, I would like to place and record my sincere thanks and appreciation to your director, Professor Dr. Ramesh Chaudhary. Then we have Emeritus Professor Roy, and Assistant Professor Gaurav Gambhir for the excellent hospitality extended to me and for all the wonderful arrangements that I've been doing. I was also in touch with this young lady. What is your name, you said? Yeah, she had sent me a mail regarding the IEEE, the student branch activity, extending an invitation to the student branch to give a talk. Thank you. We have been having a very hectic time. Yesterday, we had a very pleasant trip and visit to this religious city, places in and around, so we could earn, not we, I should say, I could earn a lot of punya thanks to you. So, major part of it goes to you all. Okay, we went and visited the memorable places in Kurukshetra, Panipat, temples and all. It was a pleasure to be here for the first time. Okay. When Professor Chaudhary, Professor Roy, and Professor Gambhir requested me about the conference, you may be aware, this college, this institute is organizing an annual conference every year to help them. I said, yes, we can do that. So it is good to come and get to know about the college, students, departments, faculty, and its past history, facilities, and all that. So that's where I decided to spend a couple of days. So we are having some conference meeting. Then she said, I should also address the IEEE student branch, and afternoon we are interacting with the faculty members to talk about research, few things. Okay. The topic of the talk, what I have decided, I made it very general because it might be a heterogeneous group. I don't know which year students, what branch, what specialization. Remotely, I didn't know the background of the students and the college. So when she sent me a mail, in a weak moment, I did, yes, I'll give a talk. But then title, I made it very general enough. So, if it is too basic for you, if you think that you already know, you can disable your interrupts and go for a sleep. I will awake at the end of the sleep. The title of the talk is Trends in Advanced Computing. So you are all what, third year students, fourth year students, second year, which year? It's all, okay? It's a heterogeneous mix. So you all have a little bit of background of computer organization, architecture, programming languages, parallel computing, high performance computing, soft computing, neural networks, mobile, wireless, stuff like that, right? So we will talk about some of these things, how the development started from good old days, okay, where we are, and what is in store. So the title, though you find here is a bit different, but the sense is same. If you looked at the advances in computers, computer organization, architecture and all that stuff, we have what is called, so we need to switch off the lights or something? Yeah, switch off the lights. For a computer scientist, it is a well-known picture and photograph, right? whose centenary was celebrated just a year ago. Okay. So what the title I have given that, as you can see, from transistors to teraflop computing and beyond. Okay. Why we are talking about transistors? If you look at the state of affairs or advancements in computing, high performance computing, wireless computing and all that stage, mid-1940s witnessed a very exciting thing. Okay, there is a tiny device like transistor which was invented, you know that. Okay, people who were working in a telephone company, like in Bell Labs, they were not working on computers, they were working in a telephone company. They invented a transistor. Okay, which has, after that, down the line, tremendous impact on computers, communication, electronics, wireless, you name it. Today, any device, your mobile you talk about, it has chips, VLSI chips, doing signal processing, corrections, imaging, and voice cancellations, noise cancellation, all sophisticated algorithms. The chip has probably millions of transistors. Okay, you talk about silicon and chip and stuff like that. Okay, so when we talk about a device which was so simple, you see, that was an exciting area in computing which people didn't realize. Around the same time, the celebrated mathematician John von Neumann at Princeton talked about the concept of a stored program computer. It was a simple concept. He said, the way you store data, you can as well store programs. That was very simple. But that made things very flexible. You can manipulate programs, insert instructions, delete instructions, generate new programs, okay, all that stuff. And today, people are talking about using the concept of artificial intelligence, computational intelligence, programs generating programs, hardware generating hardware, and stuff like that, okay. There are lots of exciting things. And we have some very interesting things happening around mid-40s in telephony communication also. So that period, 1945-46, was really one of the golden era of computing communications where we had exciting things happening. Okay? So if you start from that, a simple thing like transistors, as far as the computing is concerned, people witnessed what is called uniprocessor-based system. Then you talked about all sorts of names. Computer scientists are crazy. Mini, mega, maxi, mega mini, supercomputers, grid, cloud. You have all terminologies, okay? But the intent has been in all these things to improve the performance actually, okay? If you look at the advances in computer architecture, we have what is called a famous unwritten equivalent of the Parkinson's law in economics. You may be knowing Parkinson's law in economics, which informally stated says, the more salary, the more scholarship someone gave you, the more will be your expenses. So that your income and expense essentially meet. Okay. So essentially what happens in computing also, someone said, this no matter how powerful a computer you have, someone somewhere on the globe wants a computer more powerful than that. So there is an eternal greed to have faster and faster computers, smarter and smarter computers. That is where today the latest trend is people are trying to imitate the human brain and see how can you make a computer like that? Can you make? It is not a computer which does excellent numerical computations. It can't invert matrices. It can't multiply two 128-bit numbers, except for like some celebrated people like Sakuntala Devi and all who do numerical magics and all. But then it is good at recognition, classification, stuff like that. And the human brain is ultimate as far as the massive parallel and distributed computing is concerned. There are 10 power 10 or 10 power 12 neurons in the brain. Each is a processing element. Each neuron is connected to 10 power 4 of its neighbors. The total number of connections is 10 power 12 into 10 power 4 is 10 power 16. Brain doesn't have to program in C, Pascal, Fortran, Java. It doesn't need anything. And neurons die every day, but still we keep functioning. And it doesn't need force cooling. There is no question of any cooling, air conditioning, nothing. Okay. So it is ultimate as far as a parallel distributed computing system is concerned. It functions purely on biological system. Now, there is tremendous amount of research going on. Companies like Google, many of them have pumped in a lot of money, including Indian companies. One of the Infosys co-founders, okay, Chris Gopalakrishnan, has given a huge amount of money to IISc and to IIT Madras to establish a chair professorship to do brain science research. Okay, now they are telling, can we build a computer something like a human brain? Is it possible? Okay, so this is an exciting area of research. The point essentially is you are trying to build machines which are faster and faster. Now, why do you want to build machines which are faster? What is wrong with this machine? What I have? The problem is there are a class of applications which have what we call good appetite for numeric computations. Okay, you look at weather prediction. Okay, weather prediction or monsoon prediction is a solution of a complex partial differential equation which is non-linear boundary value type of problem. Okay, because if you look at the weather modeling, it is essentially minimum it has 4 independent variables at the plane XY and the altitude of the place, the village or the town or the city, time of the day. There are 4 independent variables, X, Y, G, T. The dependent variables are temperature, pressure, humidity, wind velocity, okay, all these variables. So if you try to model this thing, it is a complex nonlinear boundary value type of partial differential equations. Did you have a course in numerical solution of differential equations? I'm sure you would have had a course with engineering mathematics, graduate or so, okay. You would have had something on partial differential equations, right? Solving partial differential equations is a hell, you might have seen. Elliptic, parabolic, hyperbolic, anything you see, you can get a closed form solutions for beautiful, sweet, linear equations. But real life problems are all non-linear, complex, boundary value type. So what we do, we discretize that, convert PDEs to ordinary differential equations, again discretize, convert them to set of non-linear algebraic equations, use Newton-Raphson method and convert it to a set of linear coupled algebraic equations like Ax equals B. A is a matrix, X is a vector, B is a vector. So you try to solve for X for that. And these type of problems are encountered in signal processing, image processing, structural analysis, finite element modeling, all these areas. If you go to physics, okay, quantum chromodynamics, you talk about anything in physics, biology, lot of areas essentially depend on solution of set of linear algebraic equations. I'm sure you would have encountered. You go to electrical engineering, circuits, we get that. You go to signal and image processing, we have a lot of matrix manipulation. You go to computer graphics. Did you have a course in computer graphics? No. Computer science students? You were not taught computer graphics? You are not familiar with stuff like transformation, scaling, rotation and all that? No, not yet. So that also involves a lot of matrix manipulation. Okay? So the summary primarily is, in our scientific and engineering applications, there are a lot of vector matrix type of combinations. And these can be done very efficiently by what we call a parallel computer system. Why? You look at the dot product of two vectors. A vector A with components A1 to AN, B with components to B1 to Bn. What is the dot product? Sigma I equals 1 to n AI Bi. If I have one processor, it takes n steps because it will calculate A1 B1, A2 B2, AN Bn. Instead, if I have n processors, I will get the result in one step because one will do A1 B1, another will do A2 B2, another will do AN Bn, they will sum it up. Okay? So this is called single instruction, multiple data type of parallelism. Instruction is same, multiply. Data is different, A1, B1, A2, B2, AN, Bn. These are examples of parallelism. In our day-to-day life, we have excellent amount of parallelism we experience. Okay? We are hopefully, human brain is the ultimate example in parallelism. You are hopefully sitting and listening to me. In parallel, you are doing something. Okay? Some of you may be taking out your mobile and working on WhatsApp. Okay? So there are lots of things you may be doing in parallel in life. You look at matrix multiplications. I have a matrix A, matrix B, I take the product. When I want to get the second row, fifth column of the product matrix, I can jolly well get 4th row, 36th column, because they are independent, decoupled. You take the corresponding rows, columns and multiply, and the matrix multiplication, row column multiplication itself is a dot product, isn't it? So there is parallel. Are you able to understand?
Yes.
Yes. So these are what are called examples of parallel computing in computer architecture. I am sure it would have been taught to you. And people said, look, traditional machines, if you want to do, use weather modeling, monsoon modeling, will take days to get that. It will take more than 24 hours. So it is like talking about today's weather tomorrow, which is of no use, isn't it? When you watch the television news in the night, some news reader, young lady sits there and tells it is likely to rain, likely to be cloudy, something. It is not that they are talking out of fun and it is no black magic. Someone in the IMD department, meteorology department, is using a supercomputer. They use mathematical models, try to develop these things, solve these on a supercomputer, predict the weather and tell that. So behind that, there are hours of computing time in best of the machines. So when you talk about weather modeling, monsoon modeling, geophysical exploration, like what is there underground. So what they do, they put some detonators and explosives, pick up some signals, use signal processing techniques. Doctors and engineers who design artificial heart valves, they will say how the blood flows inside the heart and the valves. They develop a partial differential equation type of model and do that. People who develop high-speed aircrafts, okay, they do the experiments in wind tunnels, develop mathematical models, flow equations and study that. So anything to do with flow, whether flow of water, flow of blood, flow of gas, flow of air, is all a notorious problem, partial differential equations. Understand? So these are the things, there are large number of applications which we said can be parallelized and solved on what are called these parallel machines. These have given rise to the so-called concept of hyperpopulous computing. So that is why the speed of these machines is designated by how many floating point operations you can do. People talked about mega flops, they talked about flops, floating point operations per second, mega, tera, now we talk about peta, now we talk about exascale. It is just increasing like nobody's business, the 10 power business. 10 power 12, 15, 18, 21, you keep on increasing this piece. That is because there are advances in the electronics, VLSI technology. So people realize if you take a traditional electronic gate or a device or a chip, you cannot push its speed beyond a limit because TTL gates also have a signal transmission delay. You give an input, the output appears after delay, and the signal has to be transmitted over a wire. There is a delay. So you can't the delays go to zero. Unless you improve the delays or cut down the delays, speed of a processing element cannot be improved. So microprocessors, which are based on arithmetic logic unit, computations, instruction sets, you cannot increase the speed. But how do you increase the speed? You will have to have higher clock rates. If you want to have higher clock rates, means it should be able to execute instructions fast. For that you need better fabrication technology. People said, if you cannot do that, the other alternate is parallel processing or parallel computing. Is that clear? So that is where we talked about from transistors to teraflop computing, high-speed computing and beyond. And beyond is what? Of late, people are talking about because of the limitations of silicon-based systems which need cooling and all these problems. We are talking about quantum, nano, bio, and all that stuff. Of course, that is beyond the scope of this talk. We have no time. We may not be able to talk. That is what is picking up now. But if you look at, there is another paradigm, what I said, soft computing, like neural networks, fuzzy logic, and genetic algorithms, where people are trying to imitate the human brain and solve problems. Did you have any course in neural networks? No.
Neural network is beyond there.
Huh?
It is beyond their scope.
It is beyond their scope. So that is where they should learn from this type of lectures.
Yeah.
What is beyond your scope only. Okay? As I said, The human brain has so many neurons inside. The neuron is a simple processing element. There is electrochemical, like ions, potassium, sodium, ions are transmitted, a pulse is generated, we'll show the picture. Computations are done. So people say, in the brain, this is how it is done. As we mentioned, it has large number of neurons, they are connected to their neighbors, they fire and computations are done. What is the human brain is good at? As I said, not computation, classification and recognition, isn't it? For example, you have seen me today. Even if you run into me after 6 months or 1 year, 2 years, you may not know my name, you may not know from where I have come. Even if you see my hand, you will say, oh God, this was the fellow who was boring us that morning and he wouldn't allow us to leave to go for lunch. And he was just talking all crap and we were just wasting our time. You will recall wherever you see in whatever form, right? So the human brain has this concept of what is called partial association. It stores information, it retrieves pictorial information pretty easily, right? Which even the best of the computer cannot. A child of few days is able to recognize faces of granny, daddy. Nobody teaches, telling that this is the length, this is the dimension, this is how you should recognize. The child can't even speak at that stage. Okay, so it is best at pattern recognition, classification, recognition, voice recognition. Okay, by hearing the voice, the child can recognize, right? And it has what is called fuzzy characteristics. You tell the child that go to bed at about 10 o'clock, the child understands what you mean. You don't tell the child go to bed at 9 o'clock, 43 seconds, 51 minutes or something like that, right? So we use fuzzy variables, okay? So what people are trying to do is in our day-to-day life, we use many of them. For example, if you are talking to your friend, you say, park the car a bit towards the right side, okay? If you are teaching your friend how to park the car in the lane, you say, if it is a bit closer to the one on the right side, come little bit to the left and go a little bit ahead. And how you drive in the city, you say you are closer to the traffic red light point, you say start applying the brake a bit. You don't tell in terms of inches, micrometers, centimeters, okay? We use these variables and you say if it is cool, bit cooler in the room, turn on the heater a little bit more. We use all these variables called fuzzy and all that stuff, okay?
10 minutes.
Huh? No, it will take at least another hour.
Okay, sir.
We have not even gone beyond it because the main talk we have not started.
Yes, I know.
Yes. Is that all right?
Yes, sir.
Are you willing to listen?
Yes, sir.
The students are more important.
Yes, sir.
Okay?
Sir. So we'll do one thing.
Yeah.
We'll come back.
You have in your mind, so this fellow is a bit obese, he is overweight, okay? You extract some parameters, okay? His grey hairs on his head is more proportionately, okay? You have some metric, some ideas you have, okay? Right? And this is roughly the height, the facial, the appearance is like this. Some features you extract, you store in the brain. Okay, next time when you run into me, okay, you try to do a template matching and this one. That is what is called in any classification problem. You extract some features. You want to identify your friend's face, signature, voice. We take what are called some features, give those features an input. That is what the human brain hopefully does. Okay, if it matches, it just classifies this is the person. Okay. That is what is used for fingerprint identification, for recognizing, identifying criminals. Okay, if you talk about terrorist detection by their facial feature detections. Okay, if the doctor wants to identify, diagnose a disease, a cardiac disease, or maybe a tumor or a cancer, looks at the plate or the image or the X-ray picture, MRI, fMRI, and PET, SPECT image, extract the features, classifies. So in a typical neural networks, primarily what you do, it is for classification. You extract some features, give it as input, and the weighted sum exceeds something, you say this is the person. Because you won't recognize me based on only one feature. you will take multiple pictures, okay? Even though you don't ask my date of birth, you will guess roughly in what range the fellow is, okay? So you will have that, all these things in a weighted form. So when you are running to me, you will try to recognize me. Is that clear?
Yes, sir.
So in a typical classification, recognizing voice, recognizing signature, recognizing faces, anything you do which is used extensively in neural network based systems, images, this is what is done. So in present day systems computing, we are worried about their functioning like human beings. It is not playing with the numbers, it should work intelligently like human beings. Is that clear?
Yes.
So what we do, we go and
Yes, sir. 10 minutes break.
so future is a tough thing. You cannot be doing that. It is one of the surest ways of being unpopular is to predict the future of technology or your own future. It is tough. Prediction is very difficult. The best way to predict the future is, as you said, is invent that. Okay? So there are many predictions which have gone wrong. Okay? Einstein said there is not the slightest indication that nuclear energy will be obtainable. We know what happened. Bill Gates, gate man, everybody has heard. He said 640K should be good enough for everybody. Okay? Today, what? 640K is nowhere which satisfies you. Right? And T.J. Watson, after whom the famous lab is known, IBM T.J. Watson Research Center, he said, I think there is a world market for maybe 5 computers. Okay? We know what is the demand now. Okay? And Ken Olsen said there is no reason anyone would want a computer in their home. Now you know PCs are used left, right, like nobody's business. Okay? So you cannot talk about technology prediction, is very difficult. So when we talk about short-term estimates, they are optimistic. In science, we talk about what can happen. Engineering and economics, we say what will happen. And in moral ethics and all, it's like what should happen, what is supposed to happen. If you look at the great advancements, they all have come from different areas. I told you, transistor was invented by a telephone company. They were not working on electronics or something like that. Telephone came. The invention came from the teacher of the deaf. Carbon dating and archaeology came in from physics. You have this mouse, okay? Its invention came that the inventor said, I got the idea for the mouse while attending a talk at a computer conference. The speaker was so boring that I started daydreaming and hit upon the idea. So normally I tell in my talks, when should people attend, that at the end of the talk at least 100 inventions will come. Because when you go, you said the fellow was so boring, I was thinking something else in parallel and I came up with a wonderful idea. When we talk about technology in general, you see, in communication-wise, good old days, you talked about telegraph, then telegraph cable, then radio, then the frequency division multiplexing, different types of multiplexing. Now what is going riding high? WDM. Okay? Wavelength division multiplexing. That is, in a single fiber, you talk about different wavelengths, different lambdas. Okay? So that you can increase the bandwidth. Essentially, you have to increase the bandwidth of transmission. It is not computing, you have to communicate, pump in and send more and more information. Okay? And costs have been coming down. Transmission capacities are increasing over the years. So we had mainframes that talked about PCs. Now what is it? Everything is embedded. You look at your washing machine, you talk about a fridge, you talk about automobile. Future automobile will have hundreds of embedded systems and computers. Okay? Everywhere. You talk a device like camera, you talk about your mobile, everywhere you talk about there is a computer sitting. Okay? So in future, even what we will have cars, automobiles, which will be driven without a driver. There will be no driver, driverless cars. Already experiment is going on. BMW, many of these companies are doing. So when such cars are driven on the highway, several hundreds and thousands of them without a driver, you can see the implication, the research which has to be done. You have to do a lot of research in robotics, obstacle avoidance, no collisions, networking, wireless communication, GPS, GPRS, control, okay, navigation, real time, everything has to be done. Okay? And these will be driven at very high speed in the highways. So the type of research which will be directed in the wireless net, and they all will be networked. Okay? Only through network they will be communicating. Okay? So it is an exciting area of research for computer scientists and communications. That is where there is also a new area which is coming up now called CPS, Cyber Physical Systems. What are cyber physical systems? Most of the real life systems are physical, right? There is a patient to which there is a computer connected to monitor something, okay? There is a plant, a process or something which is monitored. There is an aircraft which is being monitored and controlled. These are all physical systems, okay? Analog. The cyber world is a computer, digital, okay? They are all connected, the loop is closed, they are controlled. So we will have several of these things in future. What is going to happen in research, exciting things in future is CPS and what we call I, smaller case OT, Internet of Things, okay? Everything will be connected to Internet. You, me, my refrigerator, my automobile, my washing machine, everything will be connected to the Internet. So that when you are driving home from office, when you are few meters away, maybe there is the wireless sensors will automatically see in the refrigerator there is no milk, there are no eggs, okay, no vegetable, it will sense and send you a message telling that please fetch these things when you come home, okay. So it is a wireless network, it is a sensor network and all that thing. When guests come home, automatically it should sense, open the garage door and welcome them, and when they are in, automatically it should close. So there will be exciting things in the store in all walks of lives, and this is a combination of computers, communication, sensor technology, sensor networks and all that type of stuff. So what we said, there will be a computer or processor embedded everything. You are sitting and listening here, in future we will have theatre chairs, conference room chairs, which will be automatically controlled to your comfort based on the size, temperature, the time duration you are sitting and all that thing, the inclination and all that thing has to be automatically controlled. So there has to be so many sensors there. So the technology wise, we said the memory costs have been dropping and the bandwidths have been increasing and the processing speeds are increasing. There is some problem with this keyboard. So as we mentioned, things are embedded inside the heart, health, you say for medical applications, these things are embedded. You have for voice over IP applications like data voice convergence we have. We talk about RFIDs to detect objects, to track objects, to detect and track patients. Suppose your sick old parents, grandparents, you have left at home and come. You can essentially have something like an RFID, like a sensor, which detects the health status of them and it transmits over the network independent of wherever you are. So you can track them and find out their status. So essentially, people who are working in wired networks, now they are shifting to wireless networks, wireless sensor networks. Okay, it is the same protocol, same routing and all that thing, but then how many numbers you need, how do you handle security and all. Okay, so with wireless networks coming now, one of the biggest challenges we face is one of security. See, in wireless medium, there are three important problems we find. One is bandwidth. The bandwidth is not enough. Wired bandwidth, medium bandwidth is more. Wireless bandwidth is less. Second is, in wireless medium, it is the energy consumption. Okay? You have a laptop, you have a mobile, every time you are worried that you have to charge. Okay? You should have energy efficient algorithms, hardware and software. The third application is security. Wireless mediums are highly insecure. Somebody can pretend to be a transmitter, pretend to be a receiver, you can eavesdrop and listen to the communication, and these things are abstracted, there are already hindrances and all that. As was mentioned by someone, the future war, the enemies will fight not by bombs and missiles and attacking them. It is the hackers who will make life miserable for you. Today imagine the airline reservation system, railway reservation system, banking system and power grid operation system in this country comes to a grinding halt. You don't need a war in this country. There will be chaos there. Okay? You can't do anything. You can't book tickets, you can't move anywhere, no banking transaction, nothing. So it is the hackers who will make your life miserable in future. So every time you are nervous, you are doing some commerce, some e-commerce transaction over the net, passing your credit card number, the reverse side, some 3-digit number, you are nervous what will happen. Okay? But then the question is, in wireless technology, when you are depending more and more, it is highly insecure. Security is the thing which has to be researched. So for young students, researchers, academicians, I think the area to look at in future is security of wireless medium. Because in wired networks, you might have heard, one of the brute force best methods to make it secure, they say increase the word length. Make it 128 bits, make it 256 bits, make it 512 bits, so that hackers can't break. But they use best of the supercomputers. One of the applications of supercomputers is by hackers to break the code. Okay? Because you know, prime number factorization is a compute-intensive problem. Okay? It takes a lot of computer time. They use all their unused processor cycles of PCs, computers together on the network by brute force method, or brute force plus some heuristics, they try to break it. So you develop a best secure algorithm, you will see that tomorrow it will. Though a lot of research has been done in wireless technology to make them secure, still we are far off. You know, IEEE has talked about standards 802.11, A, B, C, G, I and all that thing talk. Still research is going on. And when Bluetooth started, we were all very happy. But you know what happened after a while in terms of security. Okay? We have problems in terms of wireless security. In future, we will depend more on wireless medium, and this will be one of the threats for us for security. So when we talk about an emerging technology, it goes through what is called a hype cycle. What do you mean by hype cycle? Initially, it goes through the peak. Somebody will say, oh, it is a great technology going to come up, this will happen, nano, this will replace everything, grid computing and all. Then it just comes down, the popularity, then slowly tapers. So what is shown here, what will stabilize in next 2 to 5 years? For example, grid computing. It says in next 2 to 5 years, it will stabilize. Okay? Then we talk about nano computing, maybe beyond 10 years. Because you should have devices which are cheap, you can get it. Now everybody is jumping at nano. Okay? There are only 2 nanos you talk about. One on the road, another, okay, in the laboratory. Okay? Everyone is excited on the nano. But the question is, when you talk about a nano device, it should be cheap, commercially available a device to use. Laboratory research is of no use. Okay? So it will take some time, maybe another 8 to 10 years for it to be quite popular. Similarly, grid computing. So we have been talking about high performance computing, parallel computing, clusters, network of workstations and all that thing. So over the years people talked about grid computing. In a grid computing the concept is, it is like a water grid, power grid, where you are using some device. For example, now I am using, say if I use a microphone or this device use electricity, but I don't know from where it is derived. Okay? And what is the source? Whether it is thermal or hydel, from which state it comes, nothing. So similarly, computing essentially will be available over the grid. Best of the supercomputing power, maybe there is a machine somewhere in New Zealand, somewhere in USA, somewhere in Europe, you just access it over the high-speed network. So if you look at the evolution, we went through a lot of exciting things, good old days. You talk about first written word was on the stone, then you have the typewriter, then you have textbooks, then you have emails, then now it is all tweeting. Okay? So with only few letters, characters, that is the end of the world as far as the communication is concerned. In the computer architecture, generally, the forces which play the role are technology, the programming languages, the operating systems, which essentially determine the performance, the speed of the computing system. We did mention when we talked about dot product, matrix multiplication, single instruction, multiple data. Same instruction was multiplied, data was different. And what I have in front of me staring is single instruction, single data. You can have multiple instructions, multiple data. One machine may be executing AND, another may be executing OR, another may be multiply, another may be logical NAND operation, different things in parallel. Okay? And multiple instructions, single data. That is, the instructions are different, data is same. This is a typical simple classification of parallel computing, which led over the years to the concept of high performance computing. As I said, good old days when people were using parallel machines, they were quite expensive for specific purposes, debugging was very hard, and parallel computing was more of an exception than of a norm. And many of the best companies were owned. But slowly grid computing picked up, distributed computing picked up, and now it is CUDA. Okay, companies like Envision have made it popular. You have GPU-based programming, graphics-based programming. That is what you should also start having it extensively in this college or the university. The simple facilities. We were talking with Professor Roy, the director, and all, Professor Chaudhary. You should have slowly a high performance computing, or parallel computing, or supercomputing, a laboratory activity here, so that students get some opportunity about message passing communication, MPI, paradigms like this, simple problems you solve, so that when you go out, your employment potential increases. Okay? There are jobs in this thing. Now, they are looking for programmers. Okay? Different application programmers. So, what could be an application of multiple instructions, single data? Data is one, instructions are different. You think of an application? Difficult. You think about it, okay? And let me know. What happened to this keyboard? We talked about networking. So, parallel machines were used over the years with the concept of parallel computing, number of processes. In a distributed computing, as the name implies, the computers are geographically distributed. One is in this campus, one may be NIT Kurukshetra, another may be Indian Institute of Science. They are connected through local area networks, or wide area network, or metropolitan area network, or through geographical terrestrial networks, okay, through satellites or wireless links or wired links, okay, number of these things. So each is an autonomous systems. The advantage of these things, they all will execute the operations in parallel, okay, to increase the performance and the throughput. And it is not only that, if one of the nodes or computers has failed, what it was doing can be taken care of by the other system. You know, in computer networks, one of the advantages is it has the concept of graceful degradation. If one node fails, whatever that node was doing, the others can be doing, provided the links are reliable and working. If they are not, you know how to read that. And other advantages, you can exploit the geographical time difference part. For example, right now, if you look at people in US are sleeping, so their computers are not very heavily loaded. The tasks or programs of this place can be delegated there, and they can be executed at that place. The processors can be connected in an array, in a mesh, it can be ring, in a torus. There are many types of things. With the advent of distributed computing, there are a number of terms which have come, like now network of workstations, COW, cluster of workstations like Linux, which is a public domain software, has given rise to Linux clusters. Most academic institutions, laboratories, the students, faculty work with 16-node cluster, 32-node cluster, and all that stuff. So these could be in a sort of distributed mode with processors and memories. And in computing, high performance computing, you have what is called the famous food chain, like big fish eating the small fish. That is, when supercomputers came, people thought that the microcomputers will vanish. Everybody will use that, they will use that, and everything else will go. Or the mini computers will go away, workstations will go away. Okay? But then that is not what happened. They all have, at present, if you see, a peaceful coexistence. They are there, all connected in a network mode. You can access through a grid, even the best of the computing facilities anywhere. Why do you need this breed of machines, so-called high-performance computers? We said there are a number of applications which have good appetite for number crunching. You need machines which can execute fast. Which are those? Like global warming, weather change, monsoon modeling, fluid turbulence, vehicle dynamics, quantum chromodynamics, physics, chemistry, mathematics, genome classification. There are many applications. Okay. Now people are talking about big data analytics. Okay. Huge amount of data collected. How do you use optimization methods, classification methods, decision making, medical, healthcare, and all these things to use that. Okay. In fact, today the industry has 4 words, 4 letters: SMAC, SMS. Okay. They are excited about that. What is SMAC? S is for social media. Okay. M for mobility. A for analytics, big data analytics, C for cloud. Okay. So you should be equipped with all these things. Okay. Know little bit about social media, what is happening, and all that stuff, link prediction and everything. Then big data analytics techniques. Then you have mobility, wireless communication, computing, and all that thing, and cloud. Okay. So why such a change in 10 years? It is all because of the advances in hardware. You have faster chips, which consume least amount of energy. We came from TTL to ECL, MOS, CMOS, and all that. And the law, Moore's law, that is the power of a computing system doubling every 18 months, seems to be following till now. But people say how long this will go on, because there are limitations in VLSI fabrication technology. That is where the opponents of this propose what are called quantum, nano, bio, molecular, some of these paradigms, which are good for specific applications, but we are yet to see machines based on this. So the key technologies, methods what we are seeing, system on a chip or computer on a chip, MEMS, micro-mechanical devices, ubiquitous access to fast network. That is, networks will be there everywhere. Whether you are in this campus, you are in the highway, it is all thanks to wireless networks. Okay, with the radio frequency, infrared interfaces. Even if you are driving on the highway, you can download a paper, check your mail, get your yellow papers, do everything, because we have tremendous advances wireless. Today, you go to most universities abroad, they have no longer they are talking about traditional method of network. Even if you are in cafeteria, you are walking, they say, oh, do you have a laptop? Is it wireless enabled, Wi-Fi enabled? You check your mail, do whatever. Okay? Airports, everywhere, we have seen that. Okay. So the concept of introspective computing is coming. Now, we are looking at more and more what is called biology, nature around us, how it does computing. What we call bio-inspired computing. Okay? We have seen an example of artificial neural network. We talked about fuzzy logic. There is something like genetic algorithms, Darwin's survival of the fittest principle, 2 good species mixing, generating a better species by parental exchange of chromosomes and all. So we mix 2 good schemes and generate what is called a better scheme or a better solution. So these are the things which are coming up. We are looking at biology. We don't have time in this talk to talk about that, like particle swamp optimization, bacterial optimization, And there are large number of them. Ant colony optimization. A colony of ants, how they proceed to fetch their food, their leisure part. If you ask a computer scientist, you will say, let me use Dijestra's algorithm to find the shortest path. Ants don't use Dijestra's method, nothing. They have their heuristics. They lay pheromone and find out the shortest path. Okay? A school of fish, a flock of birds, they all go together. They have the vector, generate, one does, and the others follow. There is a simple algorithm, heuristics work there. We have bacteria inside the stomach, in the body. Okay, they swim, they tumble, they do all that thing, survive. There is some optimization going on, doing that. So people are looking at all these things to see how problems are solved. Optimization is done. Okay. So we are trying to look at biology and nature around us for bio-inspired computing. Okay. Probably computer scientists are exhausted with ideas. Frankly speaking, after von Neumann's exciting concept, probably nothing breakthrough has come. Okay, you are simply increasing the speed of the process, coming up with some Java someday, C# some other day, and doing all these epsilon delta tricks. But nothing really exciting or challenging is happening. Okay, putting few more processes, decomposing, telling high performance computers. But what is exciting in all these concepts? So that's where people are trying to see how Mother Nature does computing. It is doing optimization over the years. It is evolving. Best solution. That is the principle behind genetic algorithms. Okay? Genetic programming. Software generating software. Program generating programs. Hardware generating hardware. People are using these concepts. Artificial life, these notions of this time. So the trends will be reconfigurable computing, that is depending on the the load, you change the interconnection among the processors. Okay, networks will be ubiquitous. So what will be in future? Speech recognition with machines, that ability will be there, more of wireless, and you will have more biometric features. Everywhere internet. Okay, the first law of internet states that the answer is in the internet. Therefore, the quest is no longer where to find, how to work. Information retrieval intelligent is very hard. You have done, all of you, literature search. You give some keywords, you get 17 pages, 18 pages, 90 pages. By the time you are done with first page, you don't know what to do with the other one. Okay? So there is demand now for good PhDs, researchers who work on intelligent information retrieval. In future, see, I log into my system, automatically it should open the sites depending on my interest. I am interested in computer architecture, brain interface, neural network, stock market prediction, Tamil movies. So it should show all those sites. I should not log into any of those things. Okay? Automatically it should do all this. So it is more and more of what you call internally. As you can see in this simple cartoon, there was a sage, people were using to come and visit. He said, it's so nice of you to come all the way, but most people just visit my website. Okay? He says, why are you coming to me? Okay? So for everything, it is website. So the future trends will be that is system on a chip, large number of transistors, very high speeds, and portability, modularity, reusability. We didn't talk much about software. First generation, you talk about basic language, okay, user-written programs. Then we talk about symbolic languages, mnemonics. Then third generation, you talk about operating systems. Then 4G, DBMS, microcomputer languages. Fifth generation, you talk about natural, object-oriented graphics and all. But what will the future see? Future will see easy to use multi-purpose network-enabled application packages. It will be more and more wired and wireless communication. You will download free software and you will not buy MATLAB, you will not buy any software, you will license for a limited period. Why buy that? You want only for 2 weeks to solve a problem. You just license and pay that for that. And that is the concept behind cloud. Okay? You don't want to have switches, routers, hubs, programmers, systems. Okay? You just buy everything, right? Pay for the service. It is like you pay for the beautiful ringtones you get on your mobile. Okay? You keep changing for each call, you keep having the same thing, you pay for the service. That's all. So everything is service oriented here. Okay. So the other trend will be visual or conversational programming languages. Okay. More and more research will be conversational. Okay. How natural language processing based systems and visual programming will become. We will have smart homes, lightings for our mood and comfort, wireless detectors when guests come in, and it will be more of wearable computers. Today, if I go out of my home, I put on this, I put on this, put on that. After 5 years, you will be tying your computer here, you will have something like an helmet, spectacles, which will have infrared, radio frequency devices, and for your own eyes only type of things. All sorts of gadgets are already coming. There are conferences like that, a lot of research going on. This is how some of these things look. Okay? They're like spectacles, something like a helmet and all, but they are not. They are deceptive. Okay? They have all interfaces, gadgets, with best of the processor chips. You can do whatever you like. Okay? Downloading files, checking mails, and all that thing. Vision systems and all. Okay? It is like an apparel, no more. Okay? It has all sorts of interfaces and devices. Okay? So there is more of addiction to computers. This young lady goes to an expert. You say, I want my husband to pay more attention to me. Got any perfume that smells like a computer? Okay? So it is so much of addiction, PCs, computers, laptops, mobiles and all. Everywhere you are essentially getting into that. So the next generation systems will be seamless distribution, worldwide scalability, fault tolerance, self-tuning, self-configuring. What is self-configuring? See, the computers fail, okay, links fail. But in future, we will talk about systems where they will be self-healing, self-repairing, self-configuring. In advance, this will predict that this processor may fail, this link may fail, and try to reconfigure automatically by using the FPGAs. I'm sure you might have heard this, the switches of the processors, because there is a lot of free area available. And what will be challenging in future is security and resource control. Security will be biggest threat. We talked about grid computing. This is how it will look like. There is number of systems connected across the world. We talked about cloud. Okay, it is nothing to do with your cloud sourcing, raining, and all that thing. Okay, what happens over the years? Your interest has been to solve problems, but you are digressed to retain people, train people, to get computers, to have the right infrastructure, right power supplies, then air conditioning and all that thing, and upgrading the systems and all. So what people say, why do that? Instead, you pay for the service, whether network, software, platform, anything. Everything is service. Application is a software, okay? Right? So as a service, application as a service, platform as a service, all that stuff is a service, you get it in. So optical networks have been popular, their bandwidths have been increasing over the years. We talked about mobility, where you have a cell, like your cell phone, you have a tower, you keep moving from tower to tower. Instead of moving with the cell, you move with your laptop, palm top, PDAs or personal computers or any wearable computers, which are the interface. So you move from cell to cell, okay, and enter into that, and one could be communicating, downloading files, seeing voice, data, transmission. The challenges are energy conservation, mobility, because of that connections get disconnected, connectivity, quality of service, like delay, throughput, and all that thing. We said security can be compromised. Everybody is using Wi-Fi these days, right? These people are also using Wi-Fi for communication. So Wi-Fi has become very popular now. Okay, so you can have infrastructure versus ad-hoc in network. So infrastructure, there is a base station. In ad-hoc network, there is no base station. Okay, like a group of people come to a university, shopping mall, they set up their own mobile IP, start communicating. We talk about sensor networks. Now, number of sensors are thrown in the atmosphere. They pick up some signals. You can use it for tsunami prediction, flood prediction, disaster prediction. You can use them for terrorist detection by transmitting images, pictures, and all that thing. The applications are limitless. But then the research is transferring more towards that. Here you can see compare. In a conventional, it is unlimited power. Sensors is battery power. lifetime is only limited for these things. These are thrown in the atmosphere, probably with your knowledge, without your knowledge. If it is without your knowledge, extracting some parameters about you, there are some ethical issues. Okay, you can throw a sensor in a building, it can measure the vibration. If the vibration is exceeding a limit, send a message telling that earthquake is likely to strike. Okay, so there are many applications. Wildfire prediction, number of these things people have used, civilian defense, as you can see, like UAVs, large number of applications. Within buildings, vehicles, underwater, fish, okay, their habitat studies, number of applications. So what is happening? Everything is being digitized, bandwidths are exploding, devices are getting smarter and really fast. A few years ago we had mainframes as popular, then we talked about client-server paradigm, then we talked about networks. Now what is riding high is wireless. Okay, that is everything is going to be wired, wireless type of configuration, whether it's cloud, grid, whatever you may talk about. Okay, so mobility and ubiquitous computing will be the order. The handset will be the first computing device that most world will see, with everything being there. And what you started with a commercial, portable, good old cell phone, now with all these things, photo cameras, GPRS, 3G, and all that stuff, it has seen a lot of advancements. And for wireless internet to pick up, there has to be a lot of advancement which has to be done. Bandwidth has to increase 1,000 times, processing power has to increase, power consumption has to cut down, costs have to come down, then only it will be popular. IBM is talking about what is called autonomic computing, that is self-healing, self-repairing, self-configuring. Okay? There is some additional VLSI chip area available, silicon, you use that for that. So using artificial intelligence principles, computational intelligence principles, it should predict that there is a likelihood of this hardware failing. It should reconfigure automatically so that it doesn't come to a grinding halt. We have storage area network dedicated for large scale storage for network users, okay, which is also important. In the area of telecommunications, we talk many things. So what is the impact of networking and R&D and all that thing? So you cannot talk about long-term planning. Long-term planning, anything at all, it's only 6 months. Okay? And the technology is changing faster than our ability to learn. So your value or salary decreases with your experience. This is something unusual in this area. Every other area, it is the other way. Okay? Today, I tried for a job in an IT company. You know what will happen to my face. Nobody will look at my CV. Okay? So we talked about AI. It is an interdisciplinary field with psychology, computer science, engineering, linguistic, cognitive science, which is picking up pretty fast these days. But what was good old-fashioned AI, people are using a term now CI, computational intelligence, because these are algorithmic. You look at neural network, the training, learning is an algorithm, back propagation or any method. So these are computational intelligence. So what happens in the neural networks? We mentioned this is how it looks inside. There is a biological neuron, they are sitting, and there are axons, synapses, dendrites. There is an electrochemical pulse which is transmitted consisting of sodium, potassium ions. When the neuron fires, the signals are transmitted. That is how computations are done. It gets the signal, each neuron, from its neighbors. We said there are 10 power 10 or 10 power 12 neurons. Each is connected to 10 power 4 of its neighbors. But in electronics, if the fan out in TTL gate is more than 10, you say no, it right? You might have heard in your first course in electronics. Okay? There is a problem. But brain doesn't have that problem. Okay? It can drive signals to large number of its neighbors. So in a typical system like back propagation, what happens you see, I have shown number of inputs are given, x1, x2, x3, xn. They are weighted through W1, W2, Wn. The sum of products, if it exceeds a threshold, it fires. This is what I meant. You want to detect me. as an individual LFP. So what you want to do, you have to extract features x1, like my height x2, my weight x3, my gun size x4, the number of gray hairs I have x5. It is depending on you how you want to recognize me. Take those, weigh them by some factors. What should be weighed very high? Maybe the number of gray hairs or whatever it may be. Okay, weigh them, take the sum of products. If it's exceeding the threshold, you classify it to this person. You can classify faces, you can classify voices, you can classify signatures, you can classify the disease, okay? You can classify tumors, you can do any classification work like this by taking features. This is simplest of the models where there is a training classification. If it is correct, you say yes, otherwise say no, keep on changing using a learning algorithm. In backpropagation, we are not getting into that. There is what is called unsupervised. Like no one tells the biological systems like human beings and children. You don't train them. They pick up on their own. This is called unsupervised learning. By extracting some statistical features, automatically they do it. Okay? These are connected in a network. We talked about fuzzy logic, we talked about uncertainty, and we have vision. See, the computer can see, but it's a complex process. It involves large number of computations. That is also challenging area of research for robotics. But then there are still number of issues open where one has to learn the algorithms, the principles from biological systems. Agent is an assisting device helping a client to solve a problem. Today we talk about mobile agents and all that thing. I talked to you, AI is now going towards CI, computational intelligence. So in future the roles will reverse. Okay? Right? It is the other way. Okay? Security is going to be one of the toughest challenges, as I mentioned to you, like denial of service, unauthorized access, and the more we depend on wireless medium, the more will be challenges because security can be compromised. In fact, in future, if you are recruiting a system administrator, one of the probably most important qualification will be whether he is a good hacker or not. Okay, you should be able to know these tricks pretty well. There are a number of problems in this one, and those of you who are trying to take research as a career, get into problems, I think wireless security is one of the hot topics. Okay, you can talk about algorithms. The problem is, you can say you can increase the word length. The moment you increase the word length, the computation increases. Energy is more. So there is less energy in wireless already. Okay? How can you do that? There is a contradiction. So you should think of smart algorithms. And the moment you increase the word length, more computation, it takes more time, more bandwidth. You should think of good algorithms for that. How do you do hardware, software? Okay? There are what are called adaptive security. We will not talk about that. Yeah, I'm almost toward the end. We mentioned about quantum computing to essentially to have a non-silicon based approach. People have realized that your Moore's prediction of the hardware speed doubling every 18 months may not hold good eternally, and silicon devices have problems. Then we talk about non-silicon like molecular, quantum. Quantum has excellent parallelism, has been used for prime number factorization, security applications. Whether we have a general purpose system like this, only time will tell. Probably it is good for dedicated applications. Like optical computers. People said using lenses, diodes, switch level modulators, we will build optical computers, but nothing happened. Because the lens can do Fourier transform and it can do all that thing. Doesn't mean that you can build a computer which can replace. They were good for dedicated applications. Similarly, these may be good probably for specific applications in security and other things we need to see. For example, by using a typical source algorithm, factoring 1,000 digital can be done in 10 minutes, but a classical computer will take 10 billion years. Okay? So in some specific cases, they have advantages. You talk about biocomputing, molecular computing, okay, using principles of DNA, RNA, Edelman talked about computing principles, but then what was demonstrated is only traveling salesman problem was solved. You are all familiar with the traveling salesman problem. That was solved. But that doesn't mean that you can apply for everything, build a full-fledged computer using that, using the principles, okay? You can use biochemical principles, nano, quantum dots and all that thing. These are all futuristic. So what is required is a simple human interface. And as all of us know, it is programmed very strictly. Anything you try to do this way, that way, epsilon delta variations, it just doesn't answer, it comes up with a stupid response. Yeah, this is what we're desperately waiting for. To conclude, high performance computing will be driven towards metacomputing, grid computing, autonomous computing. So future may see more towards application of grid, clouds, okay, autonomous, where there is a reactive computing, okay, and you have self-healing, self-repairing and all that thing, borrowing some principles of biological systems. Mobile computing may gain importance in future, people will use it, provided we address issues of energy conservation, security, bandwidth, some of these issues. That is where there will be more research to be done and coming up with good compression, decompression algorithms, how do you conserve the bandwidth, how do you make them secure, and how do you consume least amount of energy. Okay? So for software guys who work, they say you have lesser number of instructions in the code, so that the compiler is written, less code means less instruction execution, less energy consumption. Okay? People who work in hardware, they will say low voltage ICs, 3.3 volts, 2.5 volts, and all that thing. They say either low voltage ICs, or you talk about MCMs for good packaging, multi-chip modules, and all that thing. Either packaging, low voltage, that is all for electronics people, hardware. But software guys will have to try to find out methods how you can consume least amount of energy. That is going to be an area of research. That is where today you see most of the papers in wireless and all, they will have an adjective energy efficient, okay? Energy efficient routing, energy efficient security, okay? That if it consumes even less energy by 1%, 2%, it's a great achievement. Break away from 50 plus years of machine preoccupation to a new era of this world. What do you mean by that? We had several revolutions. First revolution was agrarian, okay, based on agriculture, farmer, plows, all that thing. We didn't have to know what the plows and all. Next we had mechanical, industrial revolution, machines, okay. Your motors were used in refrigerator, here, that, but then we didn't have to bother about that. We boast about IT revolution. But in IT revolution, the unfortunate part is, you have to know so much about commands, controls, syntax, and all that thing. It is not people-oriented computing, okay? The manufacturer, the designer tries to come up with something new, thruster. You have a new version of mobile with all sorts of features, gadgets. For an old fellow like me, it is very difficult to come to terms with that. Okay? Know everything. You understand? And by the time you have understood, there is a new version as well. Okay? And if you go to the fellow manufacturer, he will say it's no more supported, you better buy a new one. And you have to learn that. So in the process, you are constantly in the cycle of unlearning and learning. Okay? Forgetting old things, learning new things. So what should happen? You should have machines which are people-oriented. Like it should be natural language processing based. You should be able to talk to it. It should be talk back. It should be touch sensitive. It should have emotion, and it can essentially convert speaker identification, speech processing. These facilities should be provided so that we are less dependent on programming, syntax, semantics, operating systems, commands, and all that. That is for a computer scientist to take care of. A common man who wants to use it is not an expert in computer science. You cannot expect him to know the idiosyncrasies of C# and C++ and all that thing. Okay? It is just not possible. It should be more user-friendly. What we said, plow for the agrarian revolution, motor for the industrial revolution, computer for information revolution. The revolution of understanding the most precious resource of earth is ourselves. So the machines should be designed keeping we the human beings in mind. So what will happen? Speech and other perceptual capabilities, knowledge access, automation, collaboration, customization will be the leading force. So that gives rise to a question: are mobile agents, Hotmail, e-commerce, Java, COM, DCOM, Corba real intellectual breakthroughs like transistors, stored program computers, are just clever epsilon delta tricks, okay, to improve here and there? Okay? Is there a really breakthrough type of work? Okay? The distant future may, we are not sure, see traditional models of computation based on concept drawn from molecular DNA quantum principles, which we need to talk about. Thank you very much. Okay? So anything you want to get my email address, anything, you visit my website www.lmpatnaik.in. It has all the details. Okay? Almost sort of my horoscope, everything else you will find. Okay? Everything about me, papers, it probably may not be updated, okay? But you will have all details. Anything. Any good questions, comments?
Thank you, sir. It is mind-boggling. I am really thankful to you, and I can say that in the history of APIIT, you are having for the first time a lecture of the standard of Indian Institute of Science by the most celebrated and most respected personality in Indian Institute of Science, not only in the world, and his Professor Patnaik. Now we invite ex-chairman of the APIIT IEEE student branch, which is Ms. Junia Antony, to propose a formal vote of thanks, please.
Good afternoon, everyone. On behalf of IEEE Student Chapter APIIT, I would like to thank Professor L.M. Patnaik for delivering such an informative lecture for us. Through this lecture, we came across various terms, advanced computing terms like BCI, CPS, IoT, fuzzy variables, etc. So it's a great privilege for us to attend such a lecture from you, sir. And I would also like to thank P.K. Roy sir, Gaurav Gambhir sir, and Ankul Singla sir, and all other IEEE student chapter coordinators for organizing and delivering us, giving us an opportunity to attend this lecture. Thank you.